Thing, probably. Yeah, so, and it is my pleasure to introduce the next speaker of today's conference, Marianna Porfido, and she will tell us about kernel estimates for a class of fractional Kolmogorov operators. So, Marianna, please.
Thank you for the introduction, and thank you, the organizers, for giving me the opportunity to give this talk today. And I will talk about this joint work with Abdelaziz Randi and Cristian Tascelli from the University of Salerno about kernel estimate for a class of fractional Kolmogorov operators. So let me introduce first the setting. So we will deal with C0 semigroups that were already mentioned a lot of time today. And so we'll denote by T our C0 semigroup. So bounded leader operator on a Banach space that has the semigroup rule and is continuous with respect to the time variable. And so when we speak about semigroup, we will also speak about generators that we will denote by A. So that is, roughly speaking, the time derivative of the semigroup. And so when we will deal with an abstract Cauchy problem of this type, and when we are in this situation, we know that this problem is well posed if and only if the generator is the generator of semigroup T. And in this case, the solution is given by the semigroup applied to the initial datum F. And in particular, we will consider semigroup on F2. And with this semigroup that that have this.
Marianna, could you please mute all the listeners?
So semigroups that have this integral representation. So so we will call this function here P the kernel of the semigroup. And of course, finding kernel estimates is important because then we will also have an estimate for the semigroup that is the solution. So we can actually estimate the solution of this kind of problems. And as the title of the talk suggested, we are interested in looking for kernel estimate for fractional operators. So actually, we will consider the fractional power of A. So A to the power of alpha. I will always call it fractional power, but actually is a power between 0 and 1. And we want to then establish estimates for the kernel associated with this fractional power. So let me briefly tell you what do I mean for this power of the operator A. So if we have a non-negative self-adjoint operator on L2, then we can consider its spectral decomposition, that is this one. And then we define the fractional power, so the power of A, we will always consider A between 0 and 1 in this way. So instead of lambda, we will have here lambda to the power of alpha. And the domain is contains all the elements in F2 such that this integral here is finite. And so to achieve our goal, so to find kernel estimate for this fractional power, we have to assume something else on the semigroup. So the very last definition of today for my talk. So we will consider symmetric Markov semigroups on F2. So they are C0 semigroups, so semigroup rule continuity, but they are also positive. So if we start with a non-negative initial datum, then we will end up with a non-negative solution of the Cauchy problem. Then they are also L-infinity contractive in the sense that this L-infinity estimate holds, and they are symmetric. So if we consider the integral of TTFG, this equals the integral of F TTG. And I want to point out that if we are in this situation, then the associated, so if we name minus A the generator of this semigroup, then the operator A is non-negative and self-adjoint. And this implies that we can consider the power and so on. Okay, my talk is divided in two parts. In the first part, we will just forget about fractionals, powers, and so on. I just want to show you how the technique we will use. So we will use weighted Nash inequalities, and I want to show you how weighted Nash inequalities are useful to find kernel estimates. And then in the second part, we will apply this technique to the fractional operators. So let's now start with a very, very easy situation. So we have a symmetric Markov semigroup. You can also think about it as a conservative semigroup. So TT1 equals 1. That means that the semigroup preserves the L1 norm. And let's start with a very, very easy Nash inequality. So this one. That, I mean, if you think about the classical Nash inequality in RD, in here, instead of the scalar product, there is just the L2 norm of the gradient of f, but now in the setting of semigroup here, we have the scalar product, so we have the integral of f AF. And what we do usually when we want to find kernel estimates starting from Nash inequalities, so the first step, that is the crucial one, is to prove an L1, L2 estimate. Meaning an estimate like this, so the L2 norm of the semigroup is bounded by a function in T, that in this case is this one, in a more general case it will be another one, and an L1 norm of F. But now we are basically done, because since the semigroup is symmetric, we also get a similar estimate, but an L2 L infinity estimate. And then by interpolation, we get an L1 L infinity estimate. But then if we have an L1 L infinity estimate, we can recall the Danforth-Pettis theorem that tells us that then there is a kernel, and the kernel has this very similar inequality. So with this same function here. So this step is the crucial one. And since the proof is very easy, I just want to show you how it works to give you an idea of this procedure. And so from weighted Nash, for a Nash inequality, we want to achieve an L1, L2 estimate for the semigroup. So what we do is to consider this function here, h, that is just the L2 norm of the semigroup square over the L1 norm of f. And since, as I was saying at the beginning, we are in a very easy example, so our semigroup is conservative, so this denominator here equals this one, so f, because the semigroup preserves the L1 norm. But now what we get that if we apply this our assumption, so the Nash inequality to the semigroup, so now instead of f here I wrote TTF, and same here and here. So if we now write this in an equivalent form, we just evaluate everything to the power of 4 over n. We divide it by this L1 norm of t. We get this. This is just manipulations. But now here, this is exactly the function h. And here, this is kind of the first derivative of h, because if you compute the first derivative, what you get is this scalar product. And then the denominator does not depend on t. So we just have to compute the time derivative of tt, or the L2 norm of tt of f. But since, as I was saying, this equals this, so we also get this denominator here. So this is the first derivative of time derivative of h. And since we get this inequality involving h and the time derivative of h, we can just kind of solve it and get this inequality, that if you now replace h by its definition here, we get our claim. Okay, so but now I just want to show you this technique in a more general example. So when we do not just have Nash inequality, but a more general inequality. So how we get this inequality? So for example, we may consider the Nash inequality with this more general form. So we just add here a term C to the L2 norm of F squared that is equivalent to this form. But now one can wonder, okay, but why just taking here the power 2 over n? Why not taking here just a non-negative, non-decreasing function? And this is exactly what we do. So we consider here, instead of this, a more general non-negative and non-decreasing function. But this is also a weighted Nash inequality, meaning that here, instead of L1 norm of F, we have the L1 norm of Fv, where V is the weight. That's why it's called weighted Nash inequality. And V has to be a Lyapunov function, so has to be non-negative in the domain of A, and has to be sort of a sub-eigen function of A. So why do we think of generalize this procedure? Because when we think about this kind of problems, our prototype of operator, the operator we have in mind, is the Kolmogorov operator. And for the Kolmogorov operator, it does not satisfy just a Nash inequality, but a weighted Nash inequality. So that's why we're trying to generalize this. And so the operator I was referring to is this one. So we have the Laplacian here and a drift term, where rho is a positive smooth function. And we are considering this operator on space L2 mu, where mu is just this weighted by this function rho. And as I was saying, A does not satisfy this classical Nash inequality, but satisfies this other inequality here. So they are kind of equivalent. And so let's look at this, and let's compare this with this. So what we have, that B is a power function, and here we do not really have this. Let's compare it. So here, you see, we have this thing. But if we assume that minus AV is less or equal than CV, that this is exactly one of the conditions of Lyapunov function, then we get a weighted Nash inequality. Just a little warning, when I was introducing this kind of inequality, I was saying that V is in the domain of A, but in this case, in this example, V is not even in L2, because let's look at this. V is this weight is rho to the power of -1/2. And if you compute the L2 norm of V with respect to this measure here, this is not finite. So V is not in L2. This means that when applying then our main theorem to this case, we will have to work a little bit more, but it is possible to apply the result also here. Okay, so what do we get? How can we generalize our procedure starting now from a weighted Nash inequality? So it is still possible to prove an L1, L2 estimate for the semigroup. This proof is kind of contained in this paper here. I mean, in this paper here, we have different estimate, weighted estimate. The Nash inequality is in a different form, but we can still get this. But what I want to highlight here is that now we have the weight. Now this estimate involves the weight. So what we would, if we want to proceed as before, we want now to apply that T is symmetric, so get an L2 L infinity estimate that is something that now we cannot achieve. So we cannot argue as before, but we can apply, we can still get Kernel estimate applying this result here that is contained in the same paper I was mentioning before. So you see this inequality, we want to apply this result for the semigroup T. So now we want to apply this result, this lemma here with, instead of Q, TT, the semigroup. And so it perfectly applies this lemma because what it says that if we have a weighted, let's put in this way, a weighted L1, L2 estimate, then we still have an estimate for the kernel, where this Q here, Q square, is the kernel of Q square, of the operators Q square. But in our case, T is a semigroup, so it has the semigroup rule. So T square is just the semigroup, but applied in the time 2T. So Q is just Q square here, just the kernel of the semigroup, applying it in time 2T. And so what we get is this estimate for A, where in here on the right-hand side, we have the weight. Okay, so now one can say, okay, so we're done. We can just apply this procedure to our fractional operator. So let's assume a weighted Nash inequality for A to the power 1/2, and we get a kernel estimate for A 1/2. But let's think about it for a moment. It means that in our examples, if we want to apply this result to the fractional operator, it means that we have to provide a weighted Nash inequality for A to the power of alpha. And as you can see, as you can guess, it's not even easy to treat this these fractional operators. They also have not a direct expression, so it's not easy to deal with them. And so to prove a weighted Nash inequality for A to the power of alpha. So that's why we need another step. So if we move to the second part now, as I was saying, it is possible to prove, to follow the same procedure for A to the power of alpha. But what is missing here is a crucial step that we were able to prove. So from a weighted Nash inequality for A, we were able to prove a weighted Nash inequality for A to the power 1/2. And if you think about our prototype operator, in that case, a weighted Nash inequality for A is available. So it's perfect because then we can apply the result. Okay, so as I was saying, this is the crucial step. So in here you can see that we have the power A to the power 1/2, and we also have that all this function B is to the power alpha. And then applying the same procedure as before, we get an L1, L2 estimate for T alpha, where T alpha is, of course, the semigroup associated to A alpha, and a kernel estimate for P alpha. And so if we collect this, all this in our main result, this is what we were able to prove. So just a brief summary of the result. So we start with a weighted Nash inequality for the operator A, and for alpha between 0 and 1, we get an estimate for the kernel associated to the operator minus A to the power of alpha, where here on the right-hand side, there is the weight function. And here, with respect to time, I just wrote here this function K. It is possible to write down an explicit expression of this function K in terms of the data of the problem, in terms of B and so on. But I mean, I didn't want to write it down too long. And this result is contained in this paper here. Okay, so now I just want to mention briefly the idea about this, the idea of this crucial step. And the idea is to start with the case alpha equal 1/2 and case C equals 0. And then from the case alpha equal 1/2, via an iteration argument, we are able to prove this same implication for this inequality for all the powers of the type 1 over 2 to the power of n. And then via a convexity argument, we can recover all the powers between 0 and 1. So now here I have a proof, but I don't know if we have time. So I want to conclude my talk by showing you in our concrete example how these estimates look like. So in case of the Kolmogorov operator. And as I was mentioning before, we need something more because V does not really satisfy all the assumptions. So the problem was that V was not in the domain of A. And so for this, we have to assume something else on rho, for example, that the Hessian of rho is uniformly bounded from above, and some other assumptions that in the examples I will show you in a moment, they are satisfied. And if we can also compute explicitly the mysterious function k we had in the general result, and in this case, this is exactly t to the power of minus d over 2 alpha. And then, so if we take rho to be of this polynomial type, so 1 plus modulo of x squared to the power of minus beta, then we get this kind of estimate, because in here we have v, but v is rho to the power of minus 1/2. So what we get is that the kernel of the fractional kernel as a polynomial growth with respect to the space variables. Whereas, for example, if rho is of this exponential type here, so a to the power of minus 1 plus modulo of x squared all up to a over 2, then we get that the kernel has like an exponential growth with respect to the space variables. And if, for example, instead rho is this other exponential type, so for a greater than 2, then also we have this similar inequality here. Okay, so I think I have 3 more minutes, right? So maybe I can go back and give you a sketch of the proof of this crucial step I was mentioning before. So we want to prove that from weighting Nash inequality for A in the where here you can see we have C equals 0, so we do not have the term involving the L2 norm of f squared, so we start with this easy case. Then we get a weighting Nash inequality for the power 1/2, also without this other term here. So this is one of the main part of the proof. And we proceed as very similarly to the basic case, because we also consider this function phi here, that is the L2 norm of T1/2, where T1/2 is the semigroup associated with the power 1/2, over Fv squared. Now, the point is that we kind of want to recover this scalar product involving A. So we have to take the second time derivative of phi. And then we can apply the Nash inequality to this semigroup T1/2. So the assumption here, we apply it to T1/2, and this is what you get. And then here, if we divide everything by the L1 norm of Fv squared, here we get exactly the second time derivative of phi, you see here. Here we get exactly phi, and here. But the problem is that this is not phi, because if we succeed in F an inequality involving only phi, so phi here, phi here, phi here, then we can kind of solve it like we did before and try to get something. But the problem is that here we do not have this. That's where the crucial point, we get to the crucial point, because
Marianna, the time is over. Huh? You have to maybe to skip the proof and then.
Yeah, okay. I just wanted to mention that this is the part in which it is important that V is in the domain of A and it is a Lyapunov function. For example, in the example of the Kolmogorov operator, this is the part we have to work with to really get this equality in that case. Okay, so this is what I wanted to say, and thank you for your